If everybody could take their seats, please. I just noticed we got ourselves a clock. So I don't have to bring my own horloge here anymore. But anyway, we agreed to within 2 or 3 minutes. So I guess we can rely on that clock now. Today, what I'm going to do is again review for you what we've been doing so far. In particular, talking about the various methods we've used, separable, direction fields, and today I'm going to teach you how to use graphical methods to get information about autonomous equations in a very, very easy way. And then next day we'll start off on linear equations. And throughout we'll be doing applications and examples. But today I hope to leave or take in the middle a little pause for question time. Some of you have emailed some very good questions. In particular, there's been a couple on how do you know when you're setting up using the slopes program, how do you know what ranges to set for the independent and dependent variable? Now, that's a very good question. And the answer is, it's up to you. Yeah. The computer is a dumb instrument. For the most part, computers are very dumb instruments. And what they're very good at is doing calculations very quickly. But as far as telling them what it is you want, that's up to you. And so you have to tell the computer roughly over what length of time do I want this solution computed for? And for what range of the dependent variable do I want it computed for? So in some sense, you have to have some a priori idea of those two settings. In other words, you want to have an idea of the range, an idea of the time span over which you would like to have a solution. And I think the best way to sort of attack that problem is to use lots of examples. Okay? There were other questions raised which are sort of the technical sort, and we'll address them as well. So anyway, so the first thing I'm going to do, let's go back to our example of mixing. Okay? And if you remember, the mixing problem was as follows. We have an input pipe, a valve here, and we're sending fluid into a tank at the rate of, and I'm going to use these general letters instead of actual numbers because I want to give you some idea what it is you're going to have to do when you come to setting ranges of time and the amount of the dependent variable. So if I have Q gallons per minute coming in, and each gallon coming in has C1 pounds in it, that comes into the tank. I have a good stir in the tank, so I keep it well stirred. It originally has G gallons, and the initial concentration was C0 pounds per gallon. Okay. I keep it well mixed. And the outward rate of flux, I'm not going to take that different. We will be looking at an example where we take it different from the input rate when we do linear equations. But I'm going to take the rate coming out to be the same. Okay? And then we let x of t be the number of pounds of salt in the tank at time t. Time t, minutes. The concentration at time t is what? Well, so first of all, we know at time t we set x of t to be the number of pounds of salt in the tank at time t. So we have to compute what's the volume of fluid at time t. And that will tell us then how to get the concentration, because we would divide the number of pounds by the number of gallons, and then we'd get the concentration. So the number of the concentration, the volume at time t, would be the initial volume, G, plus the extra in minus what comes out. But in this case, we're pumping things in and out at the same rate, both Q. So there is actually the concentration at time t will be just x of t over g. Okay? The equation we set up is essentially we compute the rate of increase of pounds in minus out. And that will give us the net increase of the number of pounds per salt per minute in the tank. The input rate, it's coming in at a rate Q gallons per minute. Each gallon of that input contains C1 pounds. So the amount coming in per minute is Q times C1. The amount going out, again, the rate out is Q. The concentration of the stuff coming out is X over G. Okay, and if we were to add the initial condition, it's as before, x of 0 would be g times c0. Okay, in other words, the amount of pounds of salt in the tank initially is the number of gallons in there initially times the number of pounds per gallon. So this is the equation we want to solve. Now you would have actual numbers in any given example, okay, but now I want to first of all, construct the solution, keeping the letters in there, so that we'll get some idea of what the relevant time scales and the relevant x scales are. Okay. Is everybody comfortable with the separable method? Okay. Okay, during question time, if you have troubles, I'm just going to write down the solution. If you have trouble seeing how it's done, in question time, I want you to raise your hand and say, can you do that on the board? And I'd be very happy to. Okay? But I'm going to tell you the answer. The answer is x of t will be g times, g times c1, and then plus x of naught minus g times c1 e to the minus q over g t. Now in the example we did, I believe the q was 2, the c1 was 1 in our example. This was 2, this was 1. I'll just put it in as x of naught minus gc1, which was 2, okay? And it was e to the minus, this was 2, this was 10, minus t over 5, okay? So now the question is, supposing you wanted to use direction fields on this, okay? Well, how much x's are going to be? Well, first of all, you can sort of see we start off with an x of gc0, okay? Now, since C0, you're interested in having C0s anywhere between, say, 0 and 2 or something like that. And the number of pounds of salt in the tank, I mean the number of gallons in the tank initially was 10. You're interested in a range of x, maybe going from 0 to 20. Okay? So that would be roughly the range of x, just to make sure that your graph is big enough to capture everything that happens. So now what is happening here? You know that essentially you start off with a certain amount of pounds of salt in the tank initially, and it's going to go to another value, either rise up to this other value, which is, we'll ask you what it is now in a minute, or descend to it. So as t gets very large, you see, this term goes away, and you know asymptotically. Asymptotically is a word we use to say what's the long time behavior of x of t. And the long time behavior of x of t, since the exponential will decay to 0, will be g times c1, which you have correctly interpreted many times as simply being the amount of the amount of number of pounds, essentially, as if you had filled it completely with the input stuff. In other words, if the input stuff was blue and this was yellow, eventually after flushing the tank for long enough, the mixture would look blue. So you would expect G times, that's the number of gallons in the tank at time t, and C1 is the number of pounds per gallon, and you'd expect GC1. Okay? So this is, in this instance, in this example, this was 10. So you would certainly need on the ordinate axis to have the 10 and maybe have the 10 in the middle. So say 0 to 20. But now the next question is, if I ran the thing, supposing I ran the thing for 1 minute. Supposing I said that was my range. The trouble with that is, after 1 minute, if I take these numbers, this is e to the minus a fifth. And that's 1 over e to the fifth. But a fifth isn't very big. So that's almost like 1. Okay? So it means that this number is still of the same order of magnitude as this number. So what you've done is only cut the beginning of the whole story. You want the whole story. So the whole story, you want to allow the thing go from its initial state to its final state. So you have to allow enough time so that this guy becomes big, and so that e to the minus that guy becomes small. So you need to have a range of time such that t is q times t over g is very large. Now when we say numbers are very large or very small, we say it's always with respect to what? Well, you see, this is a pure number. That's the whole point. It has to be a pure number because this guy, to have our units correct in the problem, this guy should be unitless. This guy is minutes. This guy is gallons per minute, and this guy is gallons. So gallons per minute divided by gallons multiplied by minutes is dimensionless. So the natural time then, you want t larger than g over c. Okay? Or g over q. Okay? This is a time. Gallons divided by gallons per minute. That's in minutes. For instance, what would g over q be for the problem here? It would be 10 over 2. Okay? So that is 5 minutes. But you want the time to be greater than 5 minutes because you want this thing to have gotten sufficiently big so this is sufficiently small so that you've reached your final state. Okay? So the natural time scale is given by this G over Q, and you want a couple of times that. Okay? Now, when I give you a little lecture later on in the term on dimensional analysis, you will see how you would have known ahead of time that the natural time scale, the time scale that's relevant in this problem, is G over Q without actually doing any of these calculations. Okay? Here, we actually did the calculation to see in what form, in what combination the time appears, and then we realize that the relevant time scale is indeed G over Q. Okay? But the whole point of using direction fields is you'll be working on equations you don't know the exact answer to. So you'll need some way of figuring out what are the relevant time scales. Now, of course, let me also suggest, and many of you did it this way, how many of you did it by trial and error in the various? Yes, and that's fair enough. That's quite okay. Trial and error is fine because computers, even though they're dumb, are very quick. So, so you very quickly realize, you know, that what ranges you have to use to get to a sensible answer. Okay, for instance, supposing the number of gallons in the tank initially G was 2, and Q was again 2 gallons per minute. Okay, what would this be then? G over Q. Supposing this was 2 now instead of 10, and this was 2, this would be 1 minute. So you'd need a couple of times 1 minute, maybe 4 or 5 minutes. So your range of T would be 5 minutes. Why is it that if you've less gallons in the tank, but the same flushing rates, why is it that you would come to the final state quicker? Well, if yes? Yeah, you flush it quicker, right? You know, if you're flushing at a certain rate and you're only flushing a total of about this 2 gallons, you flush it much quicker. Okay, so generally speaking, okay, you have to sort of make arguments like this to yourself about what you expect the solution to look like. Maybe you won't have it in explicit form, but you want some idea of what you expect to happen, and that will help you then set the ranges of dependent and independent variable. But trial and error is okay too. I mean, you can play around, but of course it may take you longer, and if you're doing a whole lot of problems, it's better to have developed some intuition beforehand as to what the correct ranges are. But now I'm going to actually, okay, any question on that? Who's is Bowen here? Bowen Liu? Yes, you were one of the chaps who, so do you understand now?
I understand.
Yeah, okay. Now, I'm now going to start introducing you to this, if you want to use, if you have an autonomous equation, namely that the f of xy in 1,7 doesn't depend on the independent variable. Okay, well, number one, we can do it by it's separable, so we can actually do the calculation. But let's take an example now. So this is the autonomous method. Okay. So what do we do? So we have something like dy by dt is f of y. F of y only. Now our example, we'll choose it from here. Okay? Now our example here is going to be 2 minus 5, sorry, 2 minus x over 5, only the x is now the y, right? Okay, so it's 2 minus y over 5. Okay. So what I'm going to do is, first of all, just draw the graph of this. I'm going to draw the graph of this f of y versus y. Okay? So this is our f of y, 2 minus y over 5. Well, at y equals 0, f is 2. It's a straight line with slope minus a fifth. And it'll hit this y-axis at y equals 10. So it comes like that. Okay? So that's 10, 0 here. Okay. Now, I claim from this picture I can tell you qualitatively everything that's going to happen to the solution. I can't give you the numbers, how quick it's going to happen, things like that, but I can tell you what is going to happen. How is that? Well, we'll take the initial condition here. Y at 0 is y0. Okay? Supposing y0 was here. Okay? Supposing y of 0 is here. I look at dy by dt, it's given by this f of y, which is this. If I take the starting point to be here, what is the sign, meaning sign, of 2 minus y over 5 at that point? Louder? Positive. How did you know it was positive? You look at the graph, right? So, if you know that this guy is positive at y0, what is the sign of the rate of change of y, dy by dt, at y0? Positive. So, if we have y0 between 0 and 10, we know f of y0 is positive. dy by dt at y0 is positive. And this tells me that y will increase as t increases, right? That's what calculus is. Okay, so where is the y going to move to from y of t? I mean from y of 0. It's going to move this way, right? Okay, half a minute later, it's here. At that value, where I've put the new x, is the f of y positive or negative? Positive. dy by dt at the new place is now again positive. So as t increases from this point, what's the y going to do? Increase. So it's going to continue doing this. And when would it stop? When it gets to 10, right? Once it gets to 10, the y doesn't increase anymore, okay? Because the equation says at y equals 10, dy by dt is 0, it stops. Okay? Now, supposing you start to the right. y0 is greater than 10. what is the sign of the 2 minus y over 5 when y0 starts greater than 10? It's negative. Okay? What's the corresponding dy by dt if f is negative? Negative. This means that y decreases as t increases, right? Right? So this says that if you start anywhere here, you go this way. Until you, what? Stop at 10. Is that what our solution suggests? Absolutely. Okay. For instance, if this was 2, and this is originally the solution, if x of 0 was 5, GC1 is 10, this would be minus 5. Okay. Sorry, this is the actual solution, so it's decaying. This guy, let's put it up here. This guy would be 2. This would be 1 over 5 here. Okay? So this is 2 minus, our x is y, in this case, 2 minus y over 5. Okay, so just by drawing the graph at the right-hand side, we can tell what's going to happen. Now, it doesn't tell you how quickly it gets to the new point, but it tells you the following. It tells you that this point, ye, say, we'll call it e, subscript e, because we'll use e for equilibrium. Okay, the equilibrium solution, okay, is 10. Once I'm at 10, I stay at 10. But when we have equilibrium solutions, we would like to know a little bit more than that they are an exact solution. We'd like to know if we started near there, would we go back there or stay near there? Okay, this brings in the notion of stability of an equilibrium solution. Okay, well, let me ask you. Supposing I am at 10, and I perturb the solution to this side. What will happen in time? Will I go back towards the equilibrium or away from it? Back towards it. How about if I start this side? Will I go back towards it or away from it? Therefore, we call this a stable equilibrium. Now, I'm going to write you down the definitions in a few moments, but I want you to get the idea first. So, it's very important. For instance, imagine my arm is a pendulum, grandfather clock pendulum. You guys have never seen a grandfather clock. I think we had this discussion before. It goes tick-tock in the night. Keeps you awake, tick-tock. Although you guys seem to be able to listen to music and sleep quite happily, so tick-tock shouldn't be too hard to... Anyway, there's two possible equilibrium solutions in the pendulum. The pendulum is hanging down, okay, like that, or up here. If it's exactly straight up, that's an equilibrium solution. Now, just from intuition, the equilibrium solution round here, if I perturb this a little bit, what happens? It'll come back if there's a bit of damping. If there's no damping, it'll just stay swinging, but it'll stay in the neighborhood. Okay? So actually there's two kinds of stability. We could start near and stay near. That's called Leopnoff stable. Or there could be a bit of damping, and then we'd swing and gradually come back to rest here. Okay? That's called asymptotic stability. Okay? We'll write these down in a minute. The examples we're looking at today, if the equilibrium is stable, it's always asymptotically stable. Okay? But a little later on, we'll be looking at situations where we have a situation like the pendulum, If the pendulum has no damping, it swings forever. But it doesn't go away from this position. It stays in the neighborhood. How about up here? Is this stable or unstable? Unstable. Even if I've damping, no matter how much damping I put in the hinge here at my shoulder, it'll still fall down. So it's unstable. Okay? And so actually isolating the equilibrium points of a dynamical system, these things are called dynamical systems, these differential equations, okay? And learning about their stability properties tells us a lot about the system. Question?
Did you say that this example here was a stable or unstable?
Well, you tell me. By stable, I would mean that if I perturb it a little bit, it goes back to the equilibrium. So in this case, what does it do? If I perturbed it a little bit this way, will it continue or go back?
It'll continue.
No, because look, if I perturb it here to here, at this point, the right-hand side of my equation, the f of y is now positive. It won't continue this way. It'll fall back. Why? Because if it's at this new y here, the right-hand side is positive. It means that at this point, dy by dt is positive, and then as t continues to increase, the y will increase. So I have given it a perturbation less than 10, but the subsequent dynamics is going to move it back to 10. Okay? It's the actual function on the right-hand side. Whether this is plus or minus tells you whether this is plus or minus. Okay? The question actually does raise an interesting point. I mean, I think you're looking at, is the slope of this plus or minus? The slope of this has nothing to do with this argument. It's just whether the graph is plus or minus in the neighborhood of the equilibrium. Let's look at another example, and we'll make it a harder example. Actually, I think I might have set this in the set homework, and I'll tell you what the solution is. But first of all, we're going to argue it out graphically. So I have dy by dt is y times 1 minus y times 2 minus y. Okay? Now, would you all take a minute and draw me the graph of the right-hand side versus y. So this is my f of y now. And I want you to draw the graph of f of y versus y. Yes.
Fy equals dy over dt?
Sorry?
Fy equals dy over dt, or are they two different things?
No, f of y represents this guy. Okay. So what does the graph of y times 1 minus y times 2 minus y look like? Anybody here whose birthday is today? This week? This month? And you're lucky because I'm going to ask the person beside you. So, can you tell me roughly what this graph looks like? Really, I just want to know, first of all, where is it going to hit the axis? Where is the graph of this guy going to hit the y-axis? In other words, where is f going to be 0? 0, 1, and 2. Very good. Okay. 0, 1, and 2. 0, 1, 2. Okay. For y less than 0, is this plus or minus? If y is less than 0, 1 minus y will always be positive. 2 minus y will always be positive. But if y is less than 0, this will be negative. So what does the graph look like? It'll come down, it'll be less than 0, up, then down, and then up again. Okay? How many got that? Great. All right. But none of you have birthdays in September. All right. Now, let's start in the different regions. Supposing, first of all, what are the equilibrium solutions? In other words, what are the solutions if I start exactly at this point, y, the solution will stay there. 0, 1, and 2. So the equilibrium solutions, so are y equals 0, ye equals 1, and ye equals 2. All right, let's start between 0 and 1. Naught is less than y0, less than 1. Okay? Now, my friend up in the back, holler out because I can't quite hear what you're saying. If I start here, what is the SIGN of f of y at that point?
Positive.
Positive, right? You just look, you see the value of f is up here, positive. So at this value of y0, what is the value of this, positive or negative?
Positive.
Positive, because it's equal to this. Okay? Therefore, as t, so I have then dy by dt is positive. Therefore, as t increases, y will increase. So, which direction will I go from here? Where will the y move? Will it move this way or this way? Will it move to the right or to the left from this point? To the right, because y is increasing, right? So it moves to the right. And you can see it keeps moving to the right until it gets to, when will it stop? 1. Supposing I start in the region 1, y0 between 1 and 2. What is the SIGN of the right-hand side if I start somewhere in here? Let's get somebody over here, this gentleman. Negative. So dy by dt is negative here. As t increases, what's y going to do? Decrease. So which direction am I going to move? To the left. And I'll end up where? At 1. So now we've decided, we've convinced ourselves, y equals 1 is an equilibrium solution, and is it stable or unstable? Stable. Because you start near, you go back. Okay? In fact, it's asymptotically stable because it just it doesn't just stay in the neighborhood, it actually goes back to the equilibrium. Okay? Now let's start at y0 greater than 2. If y0 is greater than 2, what is the SIGN of the f of y? Positive. So which way is the y going to go if I start over here? To the right. So if I start anywhere in here, I go to the left. If I start anywhere out here, I go to the right. In fact, if I start out greater than 2, where am I going to end up? Infinity. In fact, you're going to get to there infinitely quickly. Finitely quickly. You're going to get there in finite time. We'll see that from the exact solution. Okay? But this point here at equilibrium is that a stable or unstable equilibrium? Unstable. Okay? Finally, we come, supposing I start off y0 less than 0. Now, if I start off over here, what is the value, what's the sign of the graph of f at this point? Negative. So dy by dt is negative. Therefore, as t increases, y decreases. So where am I going to end up? Negative infinity. So I'll be going this way. So how about the equilibrium at y equals 0? Is that stable or unstable? Unstable. Okay? So now, for autonomous equations, you have a powerful tool. By just drawing a graph at the right-hand side, you don't have to be solving it at all. You have a method of telling you exactly what to expect. And once you know what to expect, it's often much easier to actually compute the right solution, either analytically or numerically. Let me write down the solution for you. The solution is 1 minus y all squared is 1 over 1 plus, I think it's y0 times 2 minus y0 over 1 minus y0 squared e to the 2t, I think it is. Yeah. Okay. I think that's correct. Right. Good. Now, how did I get this? How many of you have tried this problem by separable? All right, well, you have, and were you able to get this? Okay, the thing is, you get down to a point, you somehow integrate. At one stage, you have to first of all divide across by this, separate, and then you do partial fractions. And when you do partial fractions, you'll get something like the log of y times 2 minus y divided by 1 minus y all squared equals 2t plus c. Okay? So if you've got that far, that's pretty good. Now the next question is, how do you isolate the y? Now next day I'll show you how to do that. Okay? But I don't have time today to do that. Okay? But I want you to be able to do it. I mean, this is one of the harder examples. Okay, another example. There's a model in population. There's many models of population dynamics where the number of elements in the species is described by this equation. dy by dt is minus y times log y. Okay? Okay. So, what are the equilibrium solutions, first of all? What are the equilibrium solutions? 0 and 1. Very good. Very good. There's two solutions. Now, I want you, not now, but when you go home, to check, to draw yourselves a graph of that. Okay? Draw yourself the graph of log y, and then y log y, and then minus y log y. Okay? And from that graph, you'll be able to tell what happens to the solution over time. You can also actually use the separable method to solve. The solution, I think, comes out as e to the e to the t or something like that, times some constant. Okay? But that's another example well worth doing. All right, so now I'm going to write down what are the actual rules, or a few definitions of what we mean by equilibrium points, stable, that's unstable, da-da, and another concept which I will use this example for. And what I'm going to talk about now only refers to the notion of a stable equilibrium. It's interesting to know what is the set of all initial conditions, starting conditions. What is the set of all y0 for which a solution to the problem will end up at this asymptotically stable equilibrium? Okay, so if I'm going to end up here at 1, where must I start? Anywhere between 0 and 2. That's correct. Okay, so y0 between 0 and 2, that initial condition will always end up at y equals 1. So because this is very important, it's like the catchment area. You know, when you have water and a river, the catchment area is sort of the region over which all the water will flow into the river, right? Well, we call this set, the set of all initial conditions, okay, which will end up at this stable equilibrium, in this case y equals 1, we call it the basin of attraction. Now, how obvious is that? It's the basin of attraction. Okay, so it's the set of all initial conditions for which the solution starting there will end up at the stable equilibrium. Okay, so now I'm going to write down some of these definitions for you. And then we'll take 15 minutes talking about questions you might have. Okay. Equilibrium point. And we're talking about the equation dy by dt is just f of y. And I believe that has the number 27 in the book. Okay? YE is an equilibrium point of 27 if f of YE equals 0. In this case, as you correctly noted, 0, 1, and 2 are equilibrium points. Stability. So first, I'm going to give you what is known as Leopnoff stability. Leopnoff was a Russian mathematician. Now, the idea is this. The first kind of stability we're going to talk about is a weaker form. We're not going to demand that if I perturb around the equilibrium point, that the subsequent dynamics of the point is going to bring me back there. Okay? In most of our examples, that's what's going to happen in one dimension. Okay? If for first order equations. But there's a weaker notion of stability, which is not bad either. Okay? And it's the following. It says, if I start near, I stay near. In other words, if I start near this particular equilibrium point YE, will the solution for all time stay in that vicinity, or will it go away? Okay? Now, mathematicians, if you write down as a mathematical statement, start near, stay near, mathematicians, their eyebrows will go up through their hairline, you know? So, but this is what I want you to remember, because this is the correct idea. Start near, stay near. Okay? Now, there is a mathematical way of saying that, okay, which I've written down. I believe it's on page 16 of lecture notes 3 and 4. 17. Thank you. Okay? I'm not going to write it down on the board because it's in your notes. But after you've read it, I'm going to discuss it next day. And I'm going to say this horrible sounding epsilon delta language to most people sounds, oh, this is semantic and fussy, that sort of thing. But it's a rigorous way of writing down this statement. Starts near, stays near. And roughly it says, okay, roughly it says that if I start near, okay, if I want to stay within a certain epsilon, arbitrary distance from the solution, my goal, like, would be to stay, have the solution, the difference between y of t and y of e, to remain small for all time. Okay? I want to know that if I start the initial condition y0 close enough, if there exists a delta of epsilon, in other words, depending on how near I want to stay, there's another delta which is also small, but it may not be exactly the same as epsilon, such that y0 minus ye is less than delta, then if this stays true for all time, we say we're Leopnoff stable. Okay? You can sort of think of this delta of epsilon as roughly the same as epsilon, the same order of magnitude as epsilon. But it needn't be exactly, because there could be a little bit of in the dynamics, it could change it slightly. So if you want to stay within a certain prescribed distance of the equilibrium solution for all time, that the y of t will always stay there, as long as you start within a narrow band roughly the same size, as long as you can find such a narrow band that when you start there you will stay in that vicinity, then you have Leopnoff stability. Question?
So is this something that we can think of like a planetary orbit or something?
You'll have to shout louder. I'm afraid I'm rather old and a bit deaf. I'm a bit old and rather deaf.
This is something like a planetary orbit, like the Earth orbits around the sun.
This man's very good. Okay. Absolutely true, as long as no Jupiter is around. All right? It's certainly true. The orbit of the Earth around the sun is an example of a Leopnoff stable orbit. Okay? If I were to give the Earth a good kick, okay, it'll actually go into an orbit very near the other orbit. It'll stay in the vicinity of the other orbit, okay, but it won't be exactly the same orbit. But it won't go far away for all time. Now, actually, it was a big problem solved at the end of the 19th century. Well, supposing you take the influence of Jupiter or a couple of other planets. So you go from a two-body problem to a three-body or four or five-body problem. Then can you prove that this small perturbation, if you want to have the solution stay there for all time, can you prove that? And you can't. I mean, in some circumstances, you'll find that the perturbation of a third body will eventually knock this thing out of orbit. But you're quite right. The Earth's orbit around the Sun, if we just have the Earth-Sun system, is Leopnoff stable. Good question. Okay, starts near, stays near. Okay, we say an equilibrium is unstable. Okay, if it is not Leopnoff stable. Okay, so take this guy, the 2 solution here. If we start near, do we stay near for all time? Well, do we? If I start, say, just beside this, will I stay in that vicinity for all time? No, I'm going to head off to infinity. Or if I start here, I'll then head off back to 1. So that would be unstable. So now we have a notion of asymptotic stability. Asymptotic stability. Okay. And this says, if YE is Leopnoff stable, and y of t tends back to YE as time gets large, we say YE is asymptotically stable. Okay. In our cases, all the examples we've looked at, every stable point is asymptotically stable because you always go back to the equilibrium. But it won't be true for all examples we meet in various dynamical systems. Now, these qualitative ways of gleaning information from differential equations are essential, are very important. Because if you have an intuitive idea as to what to expect from your solutions, you will have a much better start in actually finding that solution analytically or numerically. You'll know what makes sense and what doesn't make sense. So these sorts of arguments are very, very useful. It doesn't give you a prescription, it doesn't give you a formula for the exact solution, but it tells you what the solution is going to do. Okay, now I promised you a little question time. One question we dealt with already. How do you pick the ranges in the slopes programs? Does anybody want to say comment on this or have any other questions in connection with that? Well, another question that came up then is this guy. And you need this for when we do linear method. Okay. I want to know what is the d by dx of the integral from 1 to x of p of s ds. Okay? Now, okay, I can't remember exactly what it is. A lot of you kind of wrote down it's this. I mean, this was already in an exponential, so we won't worry about the exponential part at the moment. You wrote down this is p of x minus p of 1. Okay, because the 1 here and the thing here. That's not right. Okay? Let's take a look at what we mean by this. If I have a graph of p of s, so this is p of s, okay, and this is s, and I want to find out the area under that graph up to between 1 and x is the integral p of s ds from 1 up to x. So supposing so this is, its derivative will be what? It'll be 1 up to x plus delta x of p of s and s ds. So minus it's the value of this at x, which is x, p of s ds, divided by delta x, and I take the limit as delta x goes to 0. Right? That's the definition of a derivative. Take the function at x plus delta x, take the function at x, subtract the 2, divide by delta x, take the limit. Now what is this? This is the ones on the bottom are the same point. So I'm taking the area in the first case from 1 to x, and the area in the second case from 1 to x plus delta x. So the difference is this bit here, right? So that would be the integral from x to x plus delta x of p of s ds divided by delta x. Okay? But this area here is roughly p of x times delta x. It's the value of p here, which is almost the same as the value of p here. We're talking about continuous functions. So this area is roughly that times this. And then when I divide by delta x, I just get p of x. Because the 1 was a constant, it doesn't come into the answer. Okay? So, the answer for, if I'm looking for the derivative of the exponential of this, it's the exponential of this times the derivative of the exponent, which we've just discovered is p of x. Okay, so how many got that? Okay, how many have questions about that still? Yes? This part.
No, because what you did down there was without the exponent.
The exponent the exponent was just this much. So this is e to the integral 1 of x p of s ds. Okay? So the derivative of this guy is going to be e to the this times the derivative of this with respect to x. Right? Because the d by dx of e to the some function of x is equal to e to the f of x times the derivative of x. Right? Okay. Are there any other questions? Yes.
Were we supposed to know to use e as the base of the exponent?
Yes, I mean, the thing said exp of this thing.
Okay, because I put it in exponential form, but I didn't think there was a specific number we had to use as the base.
What do you mean by the base?
The base to which it's raised. So I thought it would be exponent meant that it was some constant a raised to that integral.
Oh, rather than e to that.
Yeah.
Yeah. Ah, I see. Yes. Yeah. Sometimes people know that might be fair. So people. Yeah. When I talk exponential, I mean this guy. But it's certainly true that sometimes people would say if you have 2 to the x, that's exponentiating sort of 2, right? Okay. Well, if you did that and you did it correctly, because it's a lot harder, there's a log 2 comes in with respect to e, I should have to give you credit for that. Yeah?
I was wondering where we're going to be able to find the video recording of our lecture.
Oh, okay. Well, first of all, I have to look at them to check that, the old belt is properly hooked up and that sort of thing. But I do plan, Ed and Camelia have actually got them up on YouTube, and so I'm going to give you that address. And as long as you don't laugh too hard at it, if it's helpful to you, you're very welcome. I mean, we'll have to do a little bit of sketching and editing, but why not? I'll make it available if it's useful. If it's useful, yeah. It won't be up for any Academy Awards. But anyway. Now you must have more questions. Yes?
I don't know if we have time for this, but when we were doing like the radioactive decay example
Yes.
class, I kind of started getting lost when you started doing like A, B to the...
All right. No, we'd have time to discuss that. Okay. So let's go back and look at radioactive decay. How many of you looked up Wikipedia on radiocarbon dating? Actually, my first job was at UCLA, and I was jointly between geophysics and mathematics. And down the corridor in the chemistry department was Willard Libby, and he was a guy always for great ideas. Some correct, some not so correct. I mean, I remember he was suggesting at one stage there were ice caps on the poles of Venus. I don't think that has worked out to be right, but in any event, this idea was absolutely wonderful and brilliant, and it's as follows. It says that you have some radioactive substance. I was explaining to you that, like, carbon-14, this is an unstable isotope of carbon-12 with 6 electrons, 6 protons, okay, is actually made in the atmosphere when you bombard nitrogen with various neutrons and things like that. And it sort of enters the atmosphere. It's made constantly. It enters the system. Okay, all living systems, because essentially it goes into carbon dioxide, and then we absorb it, and it's in our bodies when we're alive at an equilibrium rate. I think I told you that, like, the ratio I think of carbon-14 to carbon-12 in your bones is like 1 in 10 to the 12 or something like that. Okay, so it's a very small amount. Okay, but it constantly decays. Okay. And but when you're still alive, it gets replenished because you're in equilibrium with the atmosphere. But once you're dead, that's it. Your bones start losing the radioactivity. It doesn't get replenished. And so you have a law that says the amount of the radioactive substance, you could think of this as the ratio of carbon-14 to carbon-12, okay? The rate of decay of this is proportional to the amount present. So the rate of decay slows as Q of T itself gets much smaller and smaller. Okay, and so we want to now, we might be given the initial conditions, Q at some time 0, we call that Q of 0. So how do you solve this? Well, if Q is not 0, it's separable. We write dq over q is minus k dt. Now we integrate. We get log of the absolute value of q is equal to minus kt plus c. Now we exponentiate, and we get modulus of q is equal to e to the minus kt times e to the c. Okay? Now it turns out, I mean, we're always just dealing with positive amounts. Okay? So the absolute value here of q is the same as q. So I have, but if we didn't know that, we'd have to allow this to be both signs. So we would take e to the c, which is always a positive constant. We would say we can have plus or minus. So the general solution of this is q of t is a e to the minus kt. Now is that okay? Is that clear?
What does the A represent?
A is the free constant. It's the e to the constant. Okay?
Because it's plus or minus. So you're
It's
saying-
plus or minus. Although in this case, because of context, you know the q is always positive. Okay? Because you start off positive and it'll never get below 0. Okay? So q is this. Now what is the a? At time 0. Okay? The left-hand side is q of 0. The right-hand side is a. Right? Because e to the minus k 0, that's 1. So then now you've determined the a. So we now know what the rule is. Q of t is q of 0 e to the minus kt. The idea now is, if you know k, and when you measure the amount of carbon-14 in the dead bone, you know what to say as a ratio of this. If you know k, you know that ratio, then you can determine the time t. The way in which we don't encode k, this decay constant, we don't encode it as k, as the rate constant for the decay. We do in other contexts where we have growth and things like that, but in this context, the way we measure this is we give you the half-life. We tell you the time it takes for this guy to decay to half of that. And that's equivalent to giving you k. And the half-life, the k, is in fact log 2 over this half-life. So when you look up the k in the book, what you get is the half-life, and so your k then is log 2 over that half-life in years. So what are the dimensions of k? What are the dimensions of k? One over years. Because if you have e to the minus kt, this product has to be dimensionless. Otherwise I can't compute. I only have e to numbers. I don't have e to oranges or e to feet, things like that. All right. Everything now is up. The answers are up. Lectures 5, 6 are up. And the answers to homework 1 and quizzes 1 and 2 and the set homework. It's all up on D2L.